Hey, how's it going? This is Will Sutherland doing Lab 5 Ceres-Earth Collision. So, in this lab, there were two initial systems. So Ceres, which was the largest asteroid in our solar system, though is now considered a dwarf planet. And there was also the Earth, System 2, which is our home. And so Earth is much more massive than Ceres. And we also have surroundings, which is the sun. And the sun is, as you know, much, much more massive than Earth. And therefore, much, much, much more massive than Ceres. So, the purpose of this lab was to collide Ceres with Earth so that the new combined mass leaves the sun's orbit. So, the goal was to determine the initial speed of Ceres necessary for the new system to leave the sun's orbit. So we assumed that it was a maximally inelastic collision, and we assumed the sun was stationary. It was the only mass in the surroundings. The Earth's orbit was circular, and that we also got to control the initial position and speed of Ceres. And so we found the initial speed was 7.9205 e to the 7th meters per second, or a little over a quarter of the speed of light. So, fundamental physics principles were the conservation of energy, delta E equals the work done by surroundings plus the heat transfer Q. And so we applied this using the change in energy of the system is equal to the change in kinetic energy of the system plus the change in gravitational potential energy of the system. And we use that to graph the energy changes over time of the different systems. And so we also had the conservation of linear momentum, which states that the change in momentum is equal to 0. And so because this is a maximally inelastic collision, we could use this to then find the initial velocity of the new mass, which is super important for determining if it will actually leave the solar system or not, because the initial velocity would need to be greater than or equal to the escape velocity for the sun. And so we also use Newton's second law, where F net equals mass times acceleration equals derivative momentum with respect to time. Just using that for our velocity update and position update in our code. So speaking of code, four main parts: initial conditions of Earth and Ceres, the while loop, first while loop, and then the initial conditions of the new combined mass, and our second while loop. So because when it collides, we only want to look at the at that mass. So we need to have two separate while loops. So these are the initial conditions. As you can see here, the I needed to upscale the radii of both the Earth and Ceres because otherwise it was way too hard to actually get them to collide. So by a scale of 20 times was enough for it to collide. I also wanted to plot the different energy graphs, change in energy graphs for the Earth, for Ceres, and for the new mass, along with just an energy graph down here of just energy versus time of the new mass. And here is just the initial constants and all that of the planets and stuff. This logical here, this was important for our loop shift, which I will explain later. There was also the system energies, kinetic energies of both systems, gravitational potential energies of both systems, and the total energies of both systems, as you can see. So the first while loop, we define the initial energies first, found the net force on the Earth, the net force on Ceres, used that to then apply Newton's second law and the position update formula, and then calculated the energy changes, as you can see there, and it continues just like that until it hits one of these if statements, these breaking conditions, where these two, as you can see, they happen. This is the goal one, though, where if the magnitude of the rate of the r the distance from Ceres to Earth is less than the Earth's radius plus Ceres' radius, then that means it's actually collided. And we also say logical equals true now. It was logical equals false before. So therefore, we use this for our second while loop, which I will show in just a second. So these are the initial conditions of the new mass. Outside of both while loops just happened. So I needed to have a new T2, delta T2, and T max 2. So just new ones for all three because they were different, two separate while loops. And it was also good because I needed a different delta T in order to actually capture or to show what better visually what is going on, because otherwise the delta T from before was way smaller because Ceres was just moving so quickly. So you can also see here, this is where we use the conservation of linear momentum to get the new velocity, and we also find our escape velocity for the sun, and use this if statement to figure out whether or not it actually escaped or not. We also found the new energies. Second while loop, literally the same as the first one. Not going to go into it very much, just with the new mass. And here are the results. As you can see, boom, collides magenta Ceres. Earth is just blue. It looks like Earth went literally nowhere. That's because Ceres is just moving so fast that it looks still. And so as you can see, it caused Earth, the new mass, to therefore it is now leaving the sun's orbit. So as you can see here, this is our energy versus time for the combined objects. So the Ceres' speed was, as I said before, 7.9205 times e to the 7th meters per second. And as you can see here, the new mass's velocity was 4.22908 e to the 4th meters per second, while the escape was 4.2269 times e to the 4th meters per second. So just a little bit bigger, which caused it to actually be able to leave the orbit, which is shown here, because we know that for escape velocity, the energy graph would look where total energy is 0 and kinetic energy is positive, decreasing down or approaching the total energy, and then potential energy, gravitational potential energy, is just the opposite of that in negative direction. But in this, I want to clarify, this is not actually at 0. This is 5.54633 e to the 30th joules. It just looks basically 0 because of this, because of the kinetic energy is so large of the new mass. So what does it mean? Why did the change in energy and changing your graph for Earth decrease as Ceres got closer and closer to colliding? So as you can see here, this was the change in energy versus time for Earth. So before the collision happened, where this right here is the end of it, so that's where they collided. So this actually makes perfect sense that it decreased, because the distance between the two masses for potential energy, in this case Ceres and the Earth, as that gets smaller, the potential energy gets larger in magnitude. But because it's negative, that means it's just getting larger in the negative direction, as you can see. And so also, why was it that the initial speed of Ceres had to be so much faster than the escape velocity of the new mass? So this is just due to it being a maximally inelastic collision, where kinetic energy was lost. A lot of it was lost. So Ceres needed an insane amount of initial speed to compensate for this loss. So in conclusion, obviously, if this were real, we would be screwed. However, you keep in mind that I needed to scale the radii of both Earth and Ceres just to be able to, just barely be able to have them collide. So it is very unlikely for large asteroids to hit Earth, let alone at such high speeds. Like, it is basically impossible. So anyway, thank you very much. Bye-bye.